All right, so in the last video, we looked at how we can take a reaction that is normally thermodynamically unfavorable, which is the formation of copper from copper sulfide. This is what we want here. We can couple it with another reaction that changes our delta G because we add these together, and now we have this reaction. We can take copper sulfide in the presence of oxygen to create copper metal in this way. That's called the coupling reaction. So that is not the only way in which we can get thermodynamically unfavorable reactions to occur. Electricity might be used, light, or coupling. One of the things that I did in my graduate work was I had a reaction that was thermodynamically favorable at room temperature, which was the removal of a carbon monoxide ligand from a metal. And I wanted to remove that carbon monoxide. So I would take my reaction contents, put it in a very small reaction vessel, seal it, and put it in a water bath, and then I would irradiate it with UV radiation, and those carbon monoxide bubbles popped off really fast. You could actually see the solution bubbling, and it would occur under those conditions. So, knowing how to assist a thermodynamically unfavorable reaction to occur is a good thing. Okay. Now, let's put all this together and look at another example. This actually comes from a AP FRQ. So what I have here is I've got two salts. I've got sodium chloride and silver chloride, and the question is, which one is more soluble, sodium chloride or silver chloride, right? So I've got, this is dissolving of sodium chloride, this is dissolving of silver chloride, and I can find my heats of formation of all of these, and I can do products minus reactants for delta H. And so I'm not going to go through that calculation, but it is going to give me 3.6 kilojoules. And then I can do the same for silver, and I get 65.7 kilojoules. I've got delta S, so I can do products minus reactants here as well, and I get 43.2 joules. And this one is 34.3 joules. Remember, this is all per Kelvin. Once I do this, if I do all of this at 298 K, I can use delta G is equal to delta H minus T delta S, and I can calculate my delta G's, and I get 9.3 kilojoules and positive 55.5 kilojoules. So let's look at our KSPs, because if we look at measuring the solubility of something, this does tell us something, but let's go ahead and verify. If we look at K, remember, the higher the K value, the more soluble it is, because the more it is going towards anions. So if I have sodium chloride in equilibrium with its two anions, if KSP is large, I'm going in that direction, and so I am dissolving easier. So let's do the calculation. I'm going to call this 1 and this 2. I'm just going to go through one calculation. Now, if I want to find K, remember we have in our formula chart this equation. It's an easy one to forget that it's there, but it's the next one in line. It's a way to relate Gibbs free energy to the equilibrium constant of your system. Again, if I want K, I'm going to rearrange all this. Ln of K is equal to negative delta G over RT. Again, I'm going to take e to each power. So that means ln of K is equal to e to the, let's write all this in, negative 9.3 kilojoules divided by 0.000. Remember, we have to change R because R is in joules. 298K. Okay, and that's going to mean that K K is equal to, made a mistake there. If I take e to the ln of K, I get K. So K is equal to all that. So K is equal to E to the 3.75, which is equal to 43. If I do the same thing for number 2, I'm going to go through the calculation again anyway. Do a better job this time. I'm going to get all the way to here because it's the same in both cases. So I'm going to say that I have this one is E to the negative 55.5 kilojoules divided by 0.008314 times 298, okay, is equal to E to the negative 22.4, which is equal to 1.9 times 10 to the minus 10. 1.9 times 10 to the minus 10, and this one is 43. So if you notice, each follows the other, doesn't it? My K value is significantly higher than this K value, which makes sense because this is a thermodynamically favorable reaction. Therefore, I should be product favored. This is a thermodynamically unfavorable reaction. Therefore, I am extremely reactant favored. In fact, silver chloride is basically insoluble. So all of these numbers are consistent with these, and you should be able to use delta H, delta S, your temperature, delta G, and maybe even K to discuss whether a reaction is favorable or not, and then compare one reaction to another.